Okay, so this lecture we are going to talk about machine translation. So, or more specifically, sequence-to-sequence model, and also we are going to introduce most popular trick in, I guess, not only in NLP, but kind of right now widely in deep learning is the attention mechanism. So we are going to introduce that. And before getting to introduce how deep learning apply to machine translation, first we are going to look at how before the neural network becomes popular, what techniques have been used for machine translation, just to get some background. So what is machine translation? I think it's easy to understand, right? So we have a source language. I think it's French here. I don't know French. Yeah, so this is a source language, and we want to map it to a target language, English. Right, so the X is our input, and we want to transform it to our target, Y. Right, so this is a sequence-to-sequence mapping. Before a neural network, right? So statistical machine translation is very popular, right? You can think of it as finding the best sequence Y. So given X, given your source sequence, you want to find the best sequence Y that maximize this probability, right? So this is a conditional probability. I think it's this. So this is you're trying to find the best sequence of your target language that maximize this conditional probability. And using the Bayes rules, we can decompose this probability into two components, right? So again, still finding the best Y, but we can use the Bayes rules to have transform it into a condition on Y, the probability condition on Y, and also on the probability of the likelihood of Y. Right. So the PY is basically the language model, right? So I think we have introduced in our last lecture about the RNN and how can we use RNN to model the languages. So the language model basically just to model the joint distribution of all the words or the joint distribution of all the words in that sentence, right? So it's just all related to PY. And then this is kind of, they call it the translation model, is given English, you can predict French, right? So you want to learn the parallel or the mapping from the parallel or pairs of data, right? To see how the phrases can be matched together from your source language to your target language. And the language model in charge of the fluency of your words, and you want to write good English, right? So this is kind of what the machine translation is targeted to do. And from that, people find the alignment is extremely important, right? I mean, the most straightforward translation you can think of is basically just do a direct one-to-one translation, maybe, right? For example, the French here, we can just find, okay, what's the corresponding English word for this, and that, right? And we just do the one word to one word kind of French to English mapping, but it won't be correct, right? Because there's these different orderings in different languages of the alignment, right? Because we may need to reorder the words to reflect the original meaning, right? So that is the alignment. So not only we need to identify the corresponding word that represents the meaning, we also need to identify the correct ordering of the words. So that's called alignment. And then in a probabilistic model, they introduce a latent variable to represent the alignment, right? To do these ordering mappings. So, well, alignment, there are many different types of alignment. Well, the easiest one can be one-to-one, right? So you can directly just do word-to-word translation, and it's kind of well aligned of all the words in the sentence. And it can happen that some words in your source language does not have a corresponding word in the translation, right? Like the here. So you don't need to put another word like correspondingly for that, right? So some words may have no counterpart for that. So this is one type of alignment, and it also can be, the alignment can be many to one, right? So what's the territory can be mapped to one word in French, and also this is mapped to one word. Right. So if you look at this, so this is the English word and this is the French words, and then you just highlight the cells while they do the mapping, right? So what's the territory is all related to this one word, right? So you can plot this relationship in this cell representation. So remember this matrix because it's very useful to map out the relationships between source and target languages, and also it's helpful to validate the translation, and also the attention is also very helpful to generate some chart like this. And yeah, so of course, if there's many to one, and then there's one to many, right? So it's maybe one word in English can be translated into like 3 words or corresponds to 3 words in French. And then it will becomes like this shape, like this one word is related to these 3 words. And this is very interesting because some words are very fertile, right? It's like hit with a pie somehow is a word in French. That's very interesting to me. I don't know why they come up with a word for this phrase in English, right? So this word has no single equivalent in English, but like if you translate it, it's like basically a phrase. That's very interesting. Is that a common action in France? I don't know. Right. So it's some words can get, can even skip. Right. So there can be crosses in the mappings. So you see the alignment is very it's actually not easy, right? So so you can maybe directly put this word corresponds to hit with a pie, but then am like kind of shows up earlier, and then you need to rearrange, even insert a word within this phrase, right? So it's not an easy task to get all the words correct in this ordering. Right? Yeah, so of course it also can be many to many. So I think it's more like a phrase to phrase translation, right? So it's don't have any many. It's like corresponds to 2 words. So it's a phrase to phrase mapping. So actually, people realize, right, because of it's like phrase to phrase makes more sense than word to word. So actually, even before the probabilistic model, people build up the phrase kind of mapping to help with the translation. So that is, I think, that would be the first version of machine translation. Okay, so that's alignment. And then people basically, although the alignment is kind of not ground truth label, people usually don't have that many labels to train. But in the probabilistic model, we can basically create a hidden variable that can, or latent variables that can help, because it kind of assumes or force some structures in the languages, and it can help build better probabilistic model. Right. So yeah, so that's the So we won't go deep into how we solve this, but that's the basic idea behind the probabilistic model, right? And then if we are able to approximate this function, say we are able to get this function in some way, and then here is basically optimization problem, right? How can we find the best y for this function? Right? It's difficult because because y is the sequence. Well, do you want to try all the possible y's so that we can find the y that maximize this, right? So if we enumerate all the possible y, well, it's too expensive, right? So people usually, to solve this, people usually impose strong independence assumption in the model. For example, for the language model, we can assume all the words are independent, and then we can decompose the py further into the language modeling, right? So like the Markov chain kind of so this probability will equals to, for example, the probability, the multiplication of all the probability of the words, for example, like that, right? So, or sequence modeling, right? So people usually put strong assumptions in the model and then use dynamic programming to find the optimal solutions. And the process to find y is called decoding, right? So yeah, I think that's easy to understand. So statistical machine translation is a huge research field before deep learning comes into play. And usually the best systems are extremely complex, as you can imagine, right? Because there are so many words and phrases and different alignments, different property of words, and words can have different meanings. Right? And then we want to model the context of the meanings as well, right? So you can see there's a whole lot of stuff to be modeled for the machine translation in order for good or workable machine translation performance. Right, and usually the system has many separated design components. Right, maybe some components works at the direct word translation, or maybe as we have introduced the dependency parsing. Right, the dependency parsing may be helpful for the machine translation. Right, so the dependency parsing can be features for the machine translation as well, right? So maybe you need a different system, a sub-system to do the dependency parsing like that, right? So you can have you can design different subsystem to extract different features that can be helpful for machine translation. So all of this to maintain this complex system, well, it's require lots of human effort, as you can imagine. And also usually you need to maintain extra resources, right? Like, for example, keep track of what are the equivalent phrases over there, right? So it's really lots of human effort to maintain a good system like this. Okay, so that is a quick introduction to statistical machine translation. Any questions on this? You can type question in the chat, or you can unmute yourself. If no question, okay, so if no questions, we move on to the neural machine translation. So actually it's I think in 14 or so it's not that far away, I guess maybe just 6 or 7 years ago. And then people want to build end-to-end pipeline for machine translation. As you can see in the statistical world, you need to build a very complex system, and then the complex system has its own subsystem to do those sub-tasks or sub-optimization. While the advantages of neural network is you can build an end-to-end solution, right? So you don't need to maintain all those subsystems. And then the architecture specifically proposed for machine translation is called sequence-to-sequence. Right? And basically it involves two recurrent neural network. So why sequence-to-sequence? Because the language is a sequence, right? So we basically map a sequence of words from your source language to a sequence of words in your target languages. Okay, so here shows what it looks like for neural machine translation. So it's a sequence-to-sequence model. Right? So basically, it's very simple structure, right? So it's basically just two RNNs. The only difference is how you pull these two RNNs together. Right? Basically, how you put it together is basically the hidden states from your first RNN is the input to your second RNN. Right? So why is this useful? Well, first, it's kind of like it helps to capture some information about your source sentence, right? So your source sentence say is a sentence of any length. You want to encode that sentence into some numerical values, right? So that sentence is transformed into a vector of numerical values through this encoder RN. Right? And then you transfer that representation to a second RN. Well, the second RN is basically just doing the language modeling, right? So every time, well, it's still conditioned on your input representation. And then every time it will going to generate a word, and then the word is going to serve as the input to the right. So it's on the second cell, right? So it's like if you unroll it, it's like it's doing this iterative process. The output becomes the input, and such we generate a sentence. Right. So this is I think that we introduced this for in the language modeling, right? So RN is specifically proposed to do the language modeling in this type. The only difference is that, well, this hidden states is conditioned on the representation from the source sentence. Right, so this is basically, they call it also is a conditioned language modeling, or conditioned on the encodings, right? And I think the cool part of this is, well, this is a sequence-to-sequence, right? Basically, this initial state, you can initialize it by any other representation. For example, if your input is image, you can replace the first RN with the CNN, right? You can replace it with the convolutional neural network, and then the learned representation is basically for that image, and that will serve as the input to your second decoding RN, and then you can see this task can be used for example, image captioning, that structure, right? So I think it depends on what's your how you want to initial your states for your decoding RN. So that shows the framework. Yeah, so this framework is very versatile, right? So it's not just for the machine translation, well, it's more specifically sequence-to-sequence. It can be used to do the summarization, right? So if you give an article, you want to generate an abstract of that article, and also dialogue, like it's more like utterance, previous utterance, and then or like question answering task, right? And then the parsing, yeah. So you want to you want to output your parse as a sequence, and also I think the dependency parsing is one type of that, right? So you want to maybe pass out what's the relationship of your words as a sequence. And then the code generation is pretty cool. It's basically you just write simple language, and then it can automatically transform it into your coding, Python, C++, or anything. Well, that will be cool. I think it will be a cool project to test with. Okay, so I think we can go a little bit deeper into the sequence-to-sequence model. And so this sequence-to-sequence model is an example of conditional language model, right? So it's conditioned on the representation, on the hidden states from your encoder, from your first RN, right? So it's basically just a language modeling. So the language modeling is like without a condition, right? So it doesn't have its initial states. But here you need to condition on the source sentence. Right? So, and here, basically the neural translation is directly calculates PYX. Right? Because here, so this is a language modeling. This is all language modeling, but condition. So without X, it's language modeling. Right? So always given the first word, you predict the second word, and given the first two words, you predict the third word. So that's language modeling. But here, because it's a machine translation, so you have to generate the words conditioned on X, right? So it's basically doing this modeling. So the question right now becomes how to train a system. Well, yeah, so first step is, of course, to get a big parallel corpus of words. So I think the objective is also very similar to language modeling, which is sum of the log probability of the words, right? Because I think the Y, say you have a vocabulary, right? So it's, for example, 1,000 vocabulary you can choose from to generate your sequence. And then the output of this is a vector of 1,000 probabilities, right? So some words get higher probability and some words have smaller probability. And then the correct word here should be he. Then you just grab the probability of he from your prediction, and then you take a neck log probability of that, right? So if he gets a probability of 1, then this will be 0, right? So you basically want to minimize this because it takes a negative. You want to minimize this objective. Right. So, and also I think last time also is like back propagation through time, right? So this whole system, the hidden states, like 2 RNs is trained all together. So it is optimized as a single system, right? So it operates end to end from Y propagates to your first RN, the states in your first RN. And then there's many tricks in terms of how you want to decode it, right? So because, well, you can always suppose it generates a vector of probabilities. And from that vector of probabilities, you can always choose a word with the maximum probability, right? That is the most greedy way to generate these words, right? So the greedy decoding. You basically just choose the most probable word at each step. But I think you all realize the problems, right? So maybe it's not the first the highest probability word. Maybe it's a second highest makes more sense in this sentence. If we just go with the greedy approach, there's no way for us to go back to choose the second highest one. Right, so the greedy decoding has no way to undo the decisions. Right, so still the same. Hit me with a pie. Well, it could be the third word. The model choose instead of me. The me may come second. Right, so but you always select the highest probability while you choose and then you cannot go back, and then you cannot find the best sequence. Because is also serve as input in the next step, and then you cannot find the best sequence. So how can we fix this? Of course, we want to keep track of what are the top words at every step. Right. So that leads to the, well, yeah, of course, there's an exhaustive search, but I don't think it's possible to do, right? So we don't want to compute all the possible sequence Y and just choose the best Y from this probability, right? It's too expensive. We all know that. And then, so basically, then we instead we choose the beam search. So I think the beam search is just to keep the k most probable solutions at each step. Right. So like earlier in the greedy, we always choose the when k equals 1, right? So we just always choose the first most probable. And here instead of 1, we can keep the 5 solutions at each step, and then we just grow that tree, right? And in the end, we can end up with a collections of sequence from that, and then we calculate the probability for the whole sequence for all the candidate sequences, and then choose the best sequence from that. Right. So it's a pretty I think if the exhaustive search is not feasible, usually the beam search, I think, in language modeling is often used for that. It's not guaranteed to find the optimal solution, but yeah, definitely it's more efficient than exhaustive search. Okay. So compared to the statistical machine translation, well, neural machine translation usually has better performance. So it's more fluent, and also it can utilize the context better. And also you don't need to handpick all the phrases mapping yourself, while it can be learned through the training. And also it is end-to-end optimization. So you don't need to optimize your subcomponents or subsystems individually and put them together, right? But the neural network solution is end-to-end. And of course, it requires much less human engineering effort. So you don't need to derive what features make sense for machine translation. Right. So it's kind of a very it's kind of a universal framework for any pairs of languages, right? Because you can imagine the features for different languages can be different also, right? But instead, using a neural network, maybe we have one solution for all different language pairs. And of course, there are some disadvantages as well. First is less interpretable. I think that is the disadvantage for all the deep learning model because yeah, it's kind of like a black box because of we don't have features. Well, most of the time the features are interpretable, and people usually rely on the features to make judgments, and they are helpful for the interpretation. Since we don't have features and the features are auto-derived, sometimes it's just hard to interpret. Right? And also it's difficult to control because you cannot put any control over there, right? It's end-to-end, so how can you control that? So you cannot specify rules or guidelines for the translations, right? You don't want the model to generate some bad languages. You don't want it to say out there. Okay, so I want to pause a little bit to hear if there's any questions on this. Okay, we can move on if no question asked. Well, everyone is waiting for the attention, I guess. And then the next question is, how can we evaluate machine translation? Well, I think it's not an easy task. I think in the NLP, in all NLP tasks, it's very challenging to to define a really good metric that can compare your algorithms and models fairly, right? I think it's still an active research field even for the evaluation in the language model in NLP task. Well, but we can work with some metrics that are helpful, right? Such as Blue score. I think Blue score is very popular in all different NLP tasks. Basically, it's just trying to evaluate how precise it is for your 1 gram, 2 grams, 3 grams, or 4 grams. Right? So the 1 gram is just each word becomes its gram, and then you match it with with the ground truth, right? So whether this word shows up in the ground truth, if it's yes, then it's accurate, right? And then you can compare it at 2 grams. So these 2 words goes together, the next 2 words goes together, and this. So you can compute the precision at 1, 2, 3, 4 grams, and then you can do a kind of like accumulated way, like average, to put them all together to get to one score. Right, so this is just it's this gram based, like 1, 2, 3, 4 gram based accuracy. Right, so you can see it's helpful, but it does not tell everything. You basically it doesn't quite tell you, I think, the structures of the sentence, and also there are so many ways you can organize you can express the same meaning with a different ordering of words, right? But you cannot like give a high score for that, right? But it is useful. Right, so a good translation can get you a poor score because there are so many different ways to translate. You cannot guarantee that it can always have a high accuracy comparing to this just gram matching, gram accuracy. But I think the Blue score is kind of commonly used. Well, some people criticize for that, but it's still kind of a standard. It's always a standard metric to check for that. More, yeah, that I'm not sure about. So in the chat, there's a questions of in the open source world. Yeah, that I'm not sure of that. Yeah, we can do some search on that. And then it here shows the trends of different types of system for neural machine translation, right? So as I mentioned in the beginning, it could be just phrase-based mapping, kind of maintainers, like you maintaining a phrase-to-phrase mapping, right? So the phrase-based, and then kind of the syntax-based, and then the neural network-based, right? So it's well, I would only say, like, during all these years, the old systems kind of stabilize in their performance, and then the neural, well, there's always a great kind of jump improvement for the neural translations. I think it relates to, well, maybe the more powerful we are able to build more powerful machine, and we are able to connect larger corpus of data, and then it all helps bring up the performance for the neural network model. So neural machine translation is the biggest success of NLP deep learning because it's really quick from the first paper published to industrial solution. So it's less than, so 14 is like 6 years ago, the first sequence-to-sequence paper published. And then 2 years later, Google already, Google Translate just switches from statistical modeling to the neural modeling, right? So it's, I think it's really fast for industrial solution. Yeah, so the originally the Google Translate used the statistical machine translation is built by hundreds of engineers over many years, and right now it's and then it's quickly outperformed, just trained by a handful of engineers in just a few months. So, but I would say, well, it's still a handful of engineers, but I guess they have quite a access to a big computing resource. I think that is maybe much more than the more than the computing resource that are used by hundreds of engineers years ago, maybe. So is the machine translation solved? Of course not. Right? So there's always many difficulties remains. So what if you cannot identify a right word for that? So out of vocabulary words. And also the domain is a critical part, because if you train your machine translation, for example, using the news article, right? So you have a news article that has both, say, English and Spanish there. And then you train your machine translation based on that. And then later on, you use the trained model on, say, translating an academic research paper. I don't think it will work well, right? So it's from totally different. One is from news, one is from, say, technology or academic papers. I don't think it will get aligned well over there. And also, it's still, because it's using RNN, there's always a challenge there to deal with longer text. How can we maintain the context of a longer text? And also how to make it work for low resource language pairs, right? Unlike English, Spanish, French, or these popular languages, we can get large corpus of words, but for some other languages that we don't have such privilege, right? So can we improve the performance for those low resource language pairs? And also, how to encode the common sense in the machine translation is still hard, right? Especially if there's idioms and the stories there, and then because the translation of that language does not only depend on the context of the source language, but also depends on maybe some stories long ago, or some common that everyone knows about, right? But it's not captured here, right? So I don't know what this means, but I don't know why this translates into has no hair on the tongue. Yeah, his face went down, so that's I think that's quite straight, a direct translation of that. And also the machine translation can pick up biases in the data. Yeah, people usually say for machine learning, so this is not just for machine translation, right? So if there is bias in your data, usually the machine learning models can kind of magnify the biases by 3 times more than in your data, right? So for example, like in the source languages, it doesn't specify any gender here, but in the translation, it will give she for the nurse and he for the programmer over there. And then so this actually is the news. So if you go to that link, I think it's a very interesting article to read. So why is Google Translate spitting out these religious prophecies? Right? So you just type some random words like AG. But I double checked, they have fixed this. So no need to try on your end. When I see this, I go, oh, have they fixed this? Yeah, so they have fixed this. So like originally people capture that, right? So if you just type these random words, you will gives you a nice sentence of so you have no idea where this is from, right? So maybe just because of the cranky of neural network and it's hard to control, and then sometimes it just generate this random sentence. So neural machine translation is the flagship task for NLP. So of course there's the community is still very active to improve the models, and among many improvements, the attention mechanisms is the most important one, and that brings the best performance to a simple RM or the sequence-to-sequence model without attention. So let's introduce the attention models. So what is the problem with this architecture? Right. So basically, you just encode your source sentence into a vector representation in the end, and then that vector representation as the initial states for the next RN. Right. Well, you can see that the bottleneck is here, right? Because you really depend on the output, the final hidden states, to be reliably representing all the contextual or all the information of your source language. That's the bottleneck, right? So, and also, of course, as you know, because of the validation gradient problem, the RN usually is not very good at capturing the words at earlier, right? So if it's a long sentence and if it's the first few words, maybe the information for that is lost in the final hidden states. Yeah, so this is our information bottleneck. And we want to, also because it's static, right? So it's just one static vector. Well, the question, maybe we have some sparkling idea, like why it has to be a static vector? Maybe we can make it dynamic, right? Depends on where we add at a sentence. Maybe we can refer to a different hidden states in the source language. So that's the motivation for the attention model. So the attention provides a solution to the bottleneck problem. Right? We don't want to depend on just that one last context vector. Right? So core idea is on each step of decoder, we also we use a direct connection to the encoder to focus on particular part. Right? So originally, maybe we just depends on the last hidden states. Well, here we make a direct connection to nearly, for example, all the hidden states of the cell in the encoder. Right. So here shows the example. One simple way to do attention is through the dot product. Right. So say this is your hidden states. The first hidden state, and then you make a dot product with the first hidden state in your first RN, right? And then you do the dot product. So dot product is kind of calculate the similarity, right? So if the two vectors are more alike, and then you get a high score over there. So you just do the dot product of all that, and then from the dot product, you derive a distribution. So you just use the softmax function to turn the scores into a probability distribution. And from that, you can realize, the first word to output is highly correlated with the first word in the source sentence. So this is what it tells. It says you should utilize these hidden states really well to predict the first word. And from the distribution of this, you calculate a weighted average, right? So you get this score multiplied by these hidden states, this score multiplied by these hidden states, and then you sum up it all together. So it's kind of like a weighted average, right? For all the hidden states in your encoder, and that gives you your attention output. So this attention output, along with these hidden states, so you concatenate them together to make your first prediction. Right? So right now, this prediction not only relies on this, it also relies on like all the hidden states in your encoder, and also it relies on like the most related ones. Right? That's the mechanism for the encoder. So the same thing, right? So for the second word, here you do the inner product, and then you get a different distribution. So and heat with the pi, so the heat with the pi is all related to kind of this last word over here. Right, so that's the chart.
Question
Yeah.
for this one. So this is a short-term sentence or long? Can this do for the long sentence?
Yeah, you can do.
How long you will because the calculation
yes
is very heavy.
Yes. So well, yes, of course, you can imagine, right? So the longer the sentence, the more computation is needed. And then people right now actually propose more locally information, right? So instead of relying on the whole language, maybe you just focus on a window around the position of words. Right? So there always can be a like an efficient way to like which cells in the encoder you want to do the weighted average. Maybe you want to locate the windows of these hidden states.
Okay, thank you.
Yeah. Okay, so that's the chart, and then it can represent in equations. So basically, we have the encoder, all the hidden states for the encoder, and then we have the decoder hidden states at time t. Right, so because it's rolling out gradually, and at each t, we are going to calculate the attention scores. So for this example, the attention scores is calculated through the inner product to represent their relationship, similarity, right? And then from these attention scores, we do a softmax to transform it into a distribution function, right? So all the alpha right now will sum up to 1. And then we basically do a weighted sum of all the hidden states in the encoder, or say a window of hidden states in the encoder, and then do the sum. And finally, we get our attention output, and that attention output is concatenated to the original like decoder hidden states. So basically, the information is kind of doubled for your final prediction. So the attention mechanism significantly improves the performance because it allows the decoder to focus on certain part of the source. Right. So instead of relying on the last one hidden state from the RN encoder, right now you can basically have a kind of more like a dynamic representation of all the hidden states in your encoder. So it solves the bottleneck problem, and also it helps with the validation gradient problem, right? So it provides a shortcut to the farther away states. So usually, because in the translation, usually the first few words will rely on first few words in your source language, right? So as you can imagine, when you make a prediction of the first few words, it is going to rely heavily on the hidden states of the first few like cells in the encoder, right? And also the cool part of that attention is it automatically provides you some interpretability. So you still remember this chart, right, from the alignment, right? So the alignment actually is very important for machine translation. So actually from the attention, from the distribution, we can generate a similar map like this, right? To tell you, okay, when we predict he, what is the most important or most few important words that are important to make a prediction he. So it provides some interpretability into the model, right? So we kind of get alignment for free, but yeah, so it's, well, I think this alignment is still a little bit different, as I'm more like seeing this as contextual information, right? So what are the contextual words for he, for hit with a pie, like that? I think it's more like a contextual interpretation. Yeah, so the network can learn this all by itself. So attention right now is really getting attention. So it's actually a general deep learning trick. So not only used in sequence-to-sequence, but also right now I think also in the visual fields it's also used that. So you can use attention in many architectures and for many tasks. And here is a more general definition of attention: is you have a set of vectors, values, and then you have a query. Is another vector, right? So in the sequence-to-sequence cases, you have the values of the hidden states in your encoder, and then you have the hidden states in your decoder, and then you query all your values. Right? And then from that query, you calculate a distribution. And then from that distribution, you calculate a weighted sum of all the values, and that gives you a attention vector from the values. Right? It's kind of like a summarization of the values, or representation of most related values to this query. Right? So usually we say a query attends to the values. Right. So in this model, each decoder hidden state is the query, attends to all the encoder hidden states is the values. Right. So for any attention, you need to figure out what are the values you want to attend to and what is the query. And from this, so the weighted sum is a selective summary of the information in the values. And it's dynamic. I think that's a cool part. Right, so you always have a dynamic representation of most relevant information from the source to your prediction. And also, it's a way to obtain a fixed size of representation. Yeah, because the fixed size is basically the size of the hidden states, right? So what's the length of what's the dimension for your hidden states? And actually, it's dynamic as you move along. The decoder is dynamic, right? But you always get a fixed size representation. Depend on the query, right? So depend on the query, you can always get a fixed size dynamic representation of your source. Yeah, I think it's a very cool idea. And then this is more like a more general definition in formulas for the attention, right? So we have the values, hidden states, and then we have the queries as, I think, and then here is the attention score. So, well, this attention score, there are multiple ways to do this. So the inner product is just one way to do this, right? And usually we get attention distribution to tell you which is more important, so this distribution. And then we take a weighted sum of all the values, and then which gives you a tension output. So the only variance, I think, is mainly for how we want to define these tension scores. Yeah, so there are many different ways where you can compute this. So like there's a basic dot product, right? Just if the hidden states in your encoder and decoder, or if the hidden states of your or the dimension of your values and the dimension of your query is kind of the same, then you can directly take the dot product. But what if they are not the same dimension, right? So what if D1 does not equal to D2? And then you need to do some matrix. You need to do some matrix transformation, right? So to get a scalar value from that. So you basically add more parameters to the models to learn from, right? So it's a weight matrix, and again you put the still multiplication attention, and then through this multiplication you get one value, one numerical value, still tells you the similarity or the relationship between these two, between the value and the query. And also it can be additive, right? So W1, W2 basically transforms this dimension into the same dimension so they can sum up together. And then after that, you do an inner product. So you need to decide what's the D3, right? So it's so what is the dimension you want to map both H and S to? Because H has a dimension of D1, S has a dimension of D2, and through this multiplication, you map both vectors into D3, and then you sum it up together, and then you multiply it with another vector of D3, and then that gives you a scalar value. So usually D3 is also called the attention dimensionality. So it's a hyperparameter of how you want to map these dimensions. As you can see, so this will, of course, get you more parameters to train for the neural network. Yeah, so I think the relative advantages of disadvantages. You can read some articles, and also the assignment 4 of the course web can get you some idea. I think you need to really do some hands-on to get an idea of that, to get a feeling of that. Okay, so that is the summary of today's this description. So basically, we kind of learn a little bit about the history of the machine translation, right? From the phrase, from the statistical modeling to the neural translation, and actually rapidly just replace the original statistical ones. And we introduced the sequence-to-sequence model. It basically, I think, if you are familiar with one RN, it's very easy to put together two RNs together. And then we can add attention to the sequence-to-sequence model to make it, to focus on particular part of your input values. Right. So that's the introduction of the course materials. And then if you really want to see how we are going to implement this, so on the TensorFlow tutorials, under the text, you can see there's like word embedding. So word embedding is our first lecture. And then text generation with RN, I think, is more related to the language modeling of last lecture. And then here we have the neural machine translation with attention. So you can see how we are going to implement a sequence-to-sequence with attention over here. So if you have interest, go ahead to walk through the codes. And also, since we are planning some coding tutorials, so maybe at that we are going to walk through the codes together. If you have any questions or want to make some changes to the codes to try it out yourself, and so you can basically run it on Colab. So that's very convenient to learn and try out the codes. Um,